I will also share my screen. So this way. Yeah. So as I said, now we look at the last part, and that's the project that we're going to do. We have uploaded the project last night on Canvas, so you should be able to download the manual for the project. That's a document with a number of pages, which includes also a template code and explanations, both on the kind of the physical side, but also on the numerical side. So don't be scared. The document is quite long, but if you just kind of follow through with the steps, then it should be quite well straightforward to implement everything and run the cases that are necessary. I would also like to mention that there is, what we're looking at is both a MATLAB code for Navier-Stokes, but also we will compare that to a OpenFOAM, compare that to an OpenFOAM run of exactly the same flow case. OpenFOAM, that's an open source software that is used for CFD calculations, and it can be used for simple cases, as maybe the one that we're looking at in the project, but also for more complex cases, like really turbulence modeling cases of the flow around cars and airplanes and so on. So OpenFOAM is a very flexible method or toolkit that can be used for all kinds of simulations. Therefore, we thought it was also a good idea to include that in this course to give you at least a little bit of a taste of what it would mean to actually do CFD calculations in practice, now that you have learned a lot about the theory behind it. Yeah, so what are we going to do, or what is the purpose of the project? Well, as I was showing you also in the first hour, I can do that again by just sharing my quick PowerPoint. This. So, and I'll share this. So essentially, what we would like to look at together is the so-called lid-driven cavity. And what you see here on this video is an experiment of a lid-driven cavity. So you see there is a make my pointer to be like this. So this is an experimental facility where you have here a box where you have fluid inside. It's illuminated by a laser to create the so-called laser sheet, in which we can then, using PIV, so a specific measurement method which aims at trying to identify particle traces, and with those then the velocity. With this PIV, we can then measure the velocity field, essentially. Now, if I now run this video, which did not work like this, maybe I need to put the pointer back, not like this. Doesn't work. No, it doesn't work. So now it works. So with this experiment, we do this lid-driven cavity. So that means that we have on top of the domain, we have a belt that is moving, which essentially moves the surface wall or the upper wall up here. And inside this little box, you will then have a flow pattern emerging with the upper wall moving. Now it's very difficult to see, but now you see how there is a rotating motion inside this cavity. And it's exactly this flow case that we would like to simulate together. Now, of course, because this is a code that you develop yourself, and we need to run it on your own PC or your laptop. Therefore, we cannot make it too complicated. The domain cannot be too large. So we need to do a number of simplifications for us that we can do that within the framework of this course. But essentially, we would like to reproduce this experiment, or this experimental setup, in a numerical simulation. Now, if I share again my lecture notes, like this. So, as I said, what we would like to do now during the next few hours is to develop this code. And as I said, there's certain simplifications that we need to do. Simplifications. Mainly because you know, we have some limitations in time, we have some limitations in computer power. So we would like to have a simulation code to present or demonstrate concepts of CFD. So that means one main limitation really, or simplification, is really that you should maybe not use that code for doing production runs. It's more to understand what can be done and how things can be done in CFD. So that means, so for instance, the simplifications would be, well, we only look at incompressible flow. So no compressibility. We only look at one specific discretization scheme, so second order finite differences in space, and we only have a first order time integration. So we're just using an Euler forward scheme, which of course could all be changed. We could have higher order finite differences, higher order time integration, but this is just not within the scope of this project. However, there's also a number of things that we actually do in quite advanced ways. So if we call it the features of the code, well, we actually use sparse matrices for the pressure Poisson equation, for the pressure equations, which actually make it reasonably efficient. And of course, I mean, we have the flexibility to include also the temperature transport via a Boussinesq type of forcing. So that's a so-called active scalar, as we will discuss later on. But of course, if you want to kind of work more on this code and maybe make it a little bit more flexible in the futures, you can also think of extending this method to slightly more complex features. So I would say the potential that the code has is that we could, or you could implement a 3D formulation. You could even think of perhaps doing some implicit time stepping. That's something that we will see later on also, why this is a slight problem here, particularly when you look at low Reynolds numbers, why an implicit time stepper would actually be interesting. And of course, what you could also do is to perhaps look at some adaptive time stepping or adaptive time steps, for instance, using a CFL condition. And of course, you can also include many other things if you want to improve. But I think the reason why I'm also mentioning all of these aspects here is I would like to highlight that the code as we do it here is really meant for educational purposes. It shows the basic principles of what one or how one should write or put together a simulation code. And there's of course optimization possibilities everywhere. Okay, so what we now do during the next few hours is that today, I mean, in the next 10 minutes, I will start to discuss the physics of the cases. So first we look at the the physics, so that you understand what is it actually physically that you would like to obtain at the end of the day. Then the next step, that is then on early next week, we will look at the numerics, some selected aspects of how to implement the various methods. So in particular, how the general steps are, how the boundary conditions are implemented, and also how we actually should represent the mesh in the simulation or in the MATLAB code. And then the third step, which we will also do next week, is to looking at the results of the code. So I will demonstrate what the code is doing, and then discuss some of the physics that you can see from the results. Now, of course, we have to do that before the actual deadline of sending in the project, because we give you a time to finish the project until after the exam, so that you have enough time and you can actually focus on the exam first. But since we don't have a lecture afterwards, I need to do this presentation of the results before. Also next week, there will be an OpenFOAM tutorial given by Fermin, 2 hours, where you can follow how to set up exactly the same case in OpenFOAM, and then it should be quite straightforward based on that, and also the description that we have on the homepage to run OpenFOAM yourself. So maybe just the last thing, the deadline for the project is on the 26th of March. So please just create a report as you do for the normal homeworks and send it in by March 26th. You can work in groups as before. Just send in your own solution, and then it will be graded as well. Okay. Do you have any questions about kind of the basic idea of the project? If not, then I would like to start with just briefly demonstrating the physical case, or the physical cases, I should say, that we should look at. The first case is the lid-driven cavity. The lid-driven cavity has become I would say, a standard case within CFD for each simulation code to be able to handle and to simulate. The reason for that is that the lid-driven cavity is very, very simple in terms of the setup. It's a fully specified case in the sense that everything is just happening inside a domain. There is no boundary, there's no inflow boundary conditions, there's no outflow boundary condition. Everything just happens inside a box, essentially. So this, I would say, it's a standard CFD case. Everything is fully specified. No open boundaries. In fact, this fully specified, I need to put it in quotes a little bit, because there's one aspect that is not fully specified, and we will get back to that later on as well. But anyway, everything is in a cavity, and the idea is that we have solid walls on 3 sides. So that means on those solid walls, we will have no slip and no penetration boundary conditions. So that means that the velocity vector should be 0. And on top, we have a moving belt with a velocity of, let's say, u lid. And typically the velocity is going from left to right. If you also consider a temperature, which you can do, and that's also recommended for the PhD students in this course, then what we said is that we will have a constant temperature here below. We have a constant temperature on the top, which is a slightly different temperature. And on the side walls, we have adiabatic conditions. Adiabatic would mean that there is no heat flux in or out on the side walls. So this is the setup. And of course, as is maybe clear, if you have the ball or the lid moving from the left to the right, then because we also have a no slip boundary condition on the lid, you will then accelerate the flow in this direction. Then at this point, the flow needs to go somewhere. So it kind of goes down and forms a large vortex. Then maybe to be expected, you will get smaller vortices in these corners. Perhaps this is something that you will see later on. So this is what we would like to simulate, and then also understand the physics of it. Now, the cool thing here is also, in addition to saying that this is a standard case and it's fully specified, it actually turns out that there's only one parameter, that one non-dimensional number that will govern how the flow looks like in this case. And that is so only one parameter. And we will see that in a second exactly how we derive that, but it's only one parameter, and that is the Reynolds number. So by changing the Reynolds number from a low value to a high value, we can actually go through very different regimes. So we can start in a laminar Stokes flow type of behavior at low Reynolds numbers. Then we can get some low Reynolds number flow, which is already a little bit of nonlinear, up to a case where it's quite unsteady and you will have disturbances growing and actually staying in the flow at higher Reynolds numbers. So by just choosing or changing one parameter, the Reynolds number, you can go through all different regimes that are actually relevant for CFD. Okay. So now we talked about the actual case, and now we would like to translate that case into something that we can apply in our CFD code. So that means if you think back to the very first lecture that we had together, when specifying the physical case, at some point we need to come in and specify our mathematical model of this case, so that we also then specify the equations, the boundary conditions, and the coordinates and the geometry and all of that. And if we do that, then of course the first step would be, well, let's define a coordinate system. I put the zero or my origin of the system down here, and I will have a coordinate system that may look like this. So I have X and I have Y this way. So that would define my coordinate system. Now the next step would then be, okay, now I need to define some sizes. I need to somehow define my geometry. And of course, this box here would have a length in X. It would have a height in Y, so Lx and Ly. And then, of course, I have the various velocities. So I have the lid velocity, and I have the temperature on the top. I have the temperature on the bottom. So these are physical values that I know that I need to specify in order for running this case in a simulation. But as you know, in fluid mechanics, we don't really like to do stuff in dimensional form. We always like to do a non-dimensionalization, and that's also exactly the reason why in the end we come up with this Reynolds number. So we would like to transform everything into a non-dimensional form. So that means the first thing to consider is to do a non-dimensionalization. So that means we need to define relevant or characteristic velocity and length scales that are relevant for the problem that we want to consider. In this case, if we only consider velocity, I mean the Navier-Stokes equations, we need to define a velocity scale and we need to define a length scale that is relevant for our problem. And then together with the characterization of the fluid, which is then the viscosity, we can define a Reynolds number. Now, in this case, I guess the length scale somehow needs to be related to the geometry. And I suggest to take Ly, so the height, as the length scale. We now start with the length scale. So that means the length scale that I would choose would be Ly. And in fact, for the case right now, when we consider a square cavity, this would be also the same as being Lx. So this would be for a square cavity. The velocity scale, it's actually quite easy to find the velocity scale here because there is just one velocity scale in the problem, and that is the lid velocity. So I choose the lid velocity as being my velocity scale. And the fluid is defined with the viscosity, the kinematic viscosity. And now with the velocity, length, and the fluid scales, I can define my Reynolds number for the lid-driven cavity, which would be the U lid times Ly divided by the viscosity. And this is then also the Reynolds number that you need to add in your simulation code. And as I said before, this is the only parameter that actually affects the flow. So all the different cavities in the world that have the same Reynolds number behave actually in exactly the same way. And that is the power of non-dimensionalizations, that I'm removing all the things that are not relevant, and that is essentially the specific scales, and I'm reducing it everything to just having the relevant dynamic scales present in the final equations. So that means with those scales, velocity, length scales, I can now write my non-dimensional equations. That means I need to define my non-dimensional quantities. So that means the velocity and the length scale in non-dimensional form, which I then use in the equations. So that means, for instance, the velocity ui would then be ui star divided by my reference velocity scale, which is u lid, for instance. And here it would mean that this guy would be dimensional. And of course, this would also be dimensional. And if you divide these two dimensional quantities with each other, I get my non-dimensional velocity ui. The same thing I can do for my coordinates, which is then xi star divided by ly, the same way. And for the pressure, I can do the same thing. My non-dimensional pressure would then be my dimensional pressure, and this one is normalized with rho and u lid, u lid squared. So now I have my non-dimensional velocity, length scale, and pressure. And with all of that, I can then formulate my non-dimensional equations, which of course are the Navier-Stokes equations, dui dt plus uj dui dxj being minus dp dxi plus 1 over Reynolds d squared ui dxj dxj. And the important thing, and that's really also the conclusion for today, the important thing is that here, all of these quantities, these are now the non-dimensional ones, non-dimensionalized with the help of my reference quantities u lid and ly. And by choosing these reference quantities ULID and LY, I implicitly define also the Reynolds number, because the Reynolds number needs to be built with the same reference quantities. So that means in this equation, it's not the viscosity anymore, but rather it's the Reynolds number that shows up. Of course, that then means that now suddenly, if I'm now plotting my cavity in non-dimensional form, then it turns out that the height here is 1, because it's non-dimensionalized with the height. The width in the square cavity is also 1, and the speed of the lid is also 1, because non-dimensionalized with the ULID, with ULID. So this is now my non-dimensionalized problem, height 1, width 1, speed 1 on top. And that's the result of my non-dimensionalization. And this is also the case in exactly the way that you should implement it afterwards in the code. Okay, I think this is all I can say for today. Next week, we will then continue very briefly about the physics, and then go over to the numerical issues on how to implement that in the simulation code. But for today, this is all I wanted to say. And in the second hour, now after the break, it will be Luca taking over for the exercise session. Okay, so thank you very much for this very short hour for today, or half an hour, and we will see each other next week. Thank you.